Hi, this lesson is on the fundamental theorem of calculus. So just for convenience, I'm going to abbreviate it as FTC. There are two parts. I'm starting with part 2, which is in this pink box here. So I just want to point out that sometimes, depending on the author, part 2 is actually part 1 in some books, and vice versa. Part 1 is actually part 2. But what's important is what the theorem is saying, not necessarily what it's being called. But it's all under the umbrella of the fundamental theorem of calculus. So this theorem actually makes things a lot easier for us in terms of evaluating integrals. So part 2 says that if f of x is continuous on a closed interval from a to b, then the integral from a to b of f of x dx is capital F of b minus capital F of a. Well, what is capital F? Remember, that's the antiderivative of little f of x. And if that's true, then capital F prime of x must equal little f of x, because derivatives and integrals are opposite operations. Remember, we call this integral a definite integral. So definite integrals exist when you have limits, the a's and b's. And later on in the course, we'll talk about indefinite integrals where there are no limits. So let's evaluate the following, this is a mistake, the following definite integrals. So the first one is one that should look familiar. We've used this example a few times. We want to evaluate the integral from 0 to 1 of x squared dx. So we've used this integral to estimate the area under the curve by using left-hand endpoints, right-hand endpoints, and midpoints. Remember, midpoint gave us the best estimate. We also calculated the exact area of the curve by using the Riemann sum definition. But now we'll find the same answer that we got with the Riemann sum, which usually has quite a bit of work and algebra behind it. We'll get the same answer in just a couple of steps. So what the theorem says is that you take the antiderivative, and the antiderivative here is we're applying the anti-power rule. So you add 1 to the exponent and multiply by the reciprocal. So I have to evaluate my limits of 0 and 1 in 1/3 x cubed. Notice that once I took the antiderivative, the integral symbol went away and my limits end up on the right side of the antiderivative with this vertical bar and your lower limit at the bottom of it and your upper limit at the top of it on the right side. That's just telling you that we now have to plug those in according to what the theorem says. So we plug in 1 first and then 0, subtract the results, and you get an answer of 1/3. So if you recall, that's the same answer we got when we found this integral with the Riemann sum. Okay, so let's do another one. I have the integral from 0 to pi over 2 of 4 cosine of theta d theta. So the integral properties allow me to put the 4 in front of the integral symbol so that I'm really just looking to take the antiderivative of cosine of theta. So the antiderivative of cosine is sine. So where we have to evaluate our limits is in 4 sine of theta. And notice that our limits are again on the right side. So you always plug in the upper limit first, then subtract, plug in the lower limit. And so sine of pi over 2 is 1. 1 times 4 gives you 4. And the sine of 0 is 0. So your answer is just 4. Remember what the integral represents? This represents the area under the curve. So the area under the curve of 4 cosine of theta d theta from 0 to pi over 2 is 4 units squared. Okay, so let's look at the third example, part C here. We have the integral from 1 to 2 of t plus 1 times t minus 3 dt. Make sure you always have that differential in your integral symbol. It doesn't make sense without it. So here, this is a product. We do not have an anti-product rule. So the first thing we need to do is expand it or FOIL it out. So I have to evaluate the integral from 1 to 2 of t squared minus 2t minus 3. All right, so now I'm ready to apply my anti-power rule. So the antiderivative of t squared is 1/3 t cubed. Antiderivative of minus 2t is minus t squared. And the antiderivative of a constant, well, it's just the constant with the variable. So remember, you're just going backwards. So the derivative of negative 3t would be negative 3. So we're now going in the other direction. So now again, you write your limits on the right, the way we did here, and we plug in the upper limit first into all of the t terms, subtract, and then plug in the lower limits as the theorem indicates. So when you do the arithmetic, you have a couple of fractions and a bunch of integers. So the fractions get combined here, 7/3. The integers combine to minus 6, but we need a common denominator, which is 3. So you are subtracting 7/3 minus 18/3 for a result of negative 11/3. So as a reminder, it's okay to get a integral value that is negative, even though it represents area under a curve. Remember, with integration, the location of the area determines the sign. So any part of the graph between the curve and the x-axis that's below the x-axis would have a negative area. Any part of the curve between the x-axis and the curve that lies above the x-axis would be positive. So this indicates that the net area of both the positive and the negative parts, there's more negative than positive, so the net is a negative 11/3. Okay, let's look at D. Similar to part C above, here I have a quotient and I do not have an anti-quotient rule. So the first thing I'm going to do is divide each of the terms on top by the term on the bottom. So that's what you're seeing here, that we're going to divide each term by w to the 1/2. Remember, w to the 1/2 means the same thing as the square root of w. So what's the rule for exponents? In order to combine them, you need to remember that when you have two exponential expressions with the same base, you subtract the exponent in the numerator minus the exponent in the denominator. So that's exactly what we did in line 2 of this problem right here. I took 2, which is 4/2, minus 1/2 to get 3/2. I did the same thing for for the next term. And in the last term, well, there was nothing for you to subtract, but you can't leave that in the denominator. So you bring the w into the numerator and switch the sign of the exponent, and they are equivalent. So again, I have not integrated yet. That's why you still see the integral symbol here. We're just preparing it so that we can integrate. So in the next line, we are taking the antiderivative and we are applying anti-power rule to all 3 terms. Add 1 to the exponent and multiply by the reciprocal. That's what you see here and here. Do the same thing with 1/2. Add 1, that's 3/2, multiply by the reciprocal. And repeat the process for the last term. All right, so then in the next line, we can multiply like the 3 and the 2/5 here to get the 6/5, but we can also plug in our upper and lower limits. So so here I have 6/5 times the square root of 4 to the 5th power. Now, how did that become the square root of 4 to the 5th power? Remember that when you have an exponential expression where your exponent is a rational number or a fraction, it can get rewritten as a radical like this, which means the same thing as this. So I'm actually rewriting it in this way because it's easier to take the root before raising it to a power. So in our example, I had w to the 5/2. Well, since my denominator is 2 in 5/2, then it's just the square root of w to the 5th power. And that's exactly what you see here, except I'm plugging in my limits. So I have 6/5 square root of 4 to the 5th minus 2/3 square root of 4 to the 3rd minus 2 times square root of 4. And then you need to subtract when you plug in the lower limit. And so because I have to subtract 3 terms, I have these parentheses around the next 3 terms when you plug in 1. All right, so what I did here was I actually took the square root of 4 in the above line. So I have 6/5 times 2 to the 5th minus 2/3 times 2 to the 3rd plus 2 times 2. The square root of 1 to any power is just 1. So here, the 1 is gone because we're just multiplying by 1, but I also distributed the negative across. So that's why the signs have changed. Okay, so I end up with minus 6/5 plus 2/3 minus 2. Okay, so I did the arithmetic. That's what you see in this line. Then I combined the fractions with a denominator of 5 and the fractions with a denominator of 3, as well as the integers to get 186 over 5 minus 14/3 plus 2 over 1. LCD is 15. And so when you compute that, you get an integral value of 518 over 15. So having done some Riemann sums, I'm sure you could relate that this would be quite difficult to do with a Riemann sum. The fundamental theorem of calculus gives us a more convenient way to compute our integrals. Okay, so let's do another one. This is E. I have the integral from 1 over root 3 to root 3 of 2 over 1 plus x squared dx. All right, so the first thing I did was factor out the 2, the way I did in the previous problem. So I just have to integrate 1 over 1 plus x squared at our limits. Well, hopefully this one reminds you of something that you've memorized in the past. The antiderivative of 1 over x squared, well, that's your arctan, or your tan inverse function. So the integral has a value of 2 tan inverse of x, and that has to get evaluated at from 1 over root 3 to root 3. All right, so let's see if this is something that we could do on our own. So you plug in your numbers, and this is what you have. So those numbers happen to be part of a special triangle, the 30, 60, 90, which is what you see here. Remember, tangent is opposite over adjacent. So opposite of 60 is root 3 over 1. So that's the first one. And 60 degrees is equivalent to pi over 3. So that's why you see this here. And 30 degrees, again, tangent of 30 degrees, opposite is the 1, adjacent is the root 3, so that's what you see here. So that one corresponds to 30 degrees, which is pi over 6, which I put here. Okay, so those two fractions have to be combined, pi over 3 and pi over 6, so you need a common denominator of 6, which you see here. So you have 2 times 2 pi minus pi over 6, so it's 2 times pi over 6. The 2 and the 6 simplify, so your final answer is just pi over 3. Okay, so let's do F. So I have the integral from 1 to e squared of 3 over t dt. All right, so similar to what I said before, I'm going to put the 3 in front of the integral, so I just have to integrate from 1 to e squared of 1 over t dt. Again, hopefully this stands out as something that you recognize. That's actually the derivative of your natural log. So the antiderivative is the natural log of t, evaluated from 1 to e squared. Remember, you always have to make sure that the limits that you're going to plug into your function are in the domain. The domain of natural log is all positive numbers. 1 and e squared are both positive, so this makes sense. All right, so now we plug in our limits. So I have ln of e squared minus ln of 1 in the next line. Ln of e squared is just 2 because remember, ln and e are inverses to each other. So if it was ln of e to the x, that answer would be x. So whatever e would be raised to, ln of e to that power, well, that's what it's equal to. Ln of 1 is 0, so that's something you'd want to remember. And so you get that your integral value is just 2. Oh, sorry, I forgot the 3. Let me fix that. So your integral value is actually just 6. Okay, so let's move on. We want to sketch the area represented by the integral from -2 to 1 of 1 minus x squared dx and compute the area. So we're going to give you a visual representation of what it is that we're computing. All right, so 1 minus x squared is a parabola, and you're going to want to know what that parabola looks like at my lower limit and my upper limit. So that's definitely 2 points you want to graph. And with parabolas, you certainly need to show the vertex. So the 3 points you should be graphing are -2, -3, 0, 1, and 1, 0, which is what you see in the graph on the right. So the area that's being computed is the area between the curve and the x-axis. So the first area is this one here. That has a negative area. And this one here is positive, okay, because it's above the x-axis. So now we're going to compute and see what we get as a result. So my area is equal to the integral from -2 to 1 of 1 minus x squared dx. The antiderivative of 1 is x. The antiderivative of x squared is 1/3 x cubed. So now we're ready to evaluate that from -2 to 1. Remember, always plug in the upper limit first, then subtract and plug in the lower limit. So that's what you see in this line. And so we have 1 minus 1/3 plus 2 minus 8/3. Once you simplify, then -1/3 and -8/3, well, that's just minus 9/3. 1 plus 2 is 3. 9 divided by 3 is 3. So your area is just 0. So what that means is that these two areas are the same, except one is positive and one is negative. So they cancel each other out to just 0. Okay. Let's move on. This is the fundamental theorem of calculus, part 1. So remember, in general, the fundamental theorem of calculus gives the inverse relationship between the derivative and the integral. And so now we'll focus on part 1 here in green. So it says that if f is continuous on a closed interval from a to b, then the function g defined by g of x equal to the integral from a to x of f of t dt for x between a and b is continuous on AB, so meaning g of x is continuous on AB, and differentiable on the open interval from a to b. And this relationship is also true, that the derivative of g, and remember g is this integral, is equal to the integrand, f of x, evaluated at the upper limit. Okay, so we're going to use this theorem in order to compute some information. So given the following graph of f of t, which is here in pink, and given that g of x is defined to be the integral from 0 to x of f of t dt, we want to evaluate g of 0, g of 1, and g of 2. All right, so first let's notice that f of t satisfies the theorem. It's continuous. You can see that from the graph on a closed interval here from 0 to 4. And so g of x will represent the area under the curve of f of t, because remember, g of x is equal to this integral, and the integral represents the area. Okay, so we don't know what the function is. We can't apply antiderivative rules, but we can certainly look at the graph and use geometry. So g of 0, when x is 0, that means you're integrating from 0 to 0 of f of t dt. Well, if I'm at 0, I'm right here, which means there is no area under my curve. We also discussed this when we were talking about integral properties. If the lower and upper limit are the same value, your answer for the integral will always be 0. There is no area under the curve at a single point. Now let's see what happens when you evaluate your integral at 1. That means you're evaluating the integral from 0 to 1 of f of t dt. Well, from 0 to 1, it's this, what you see here, which is basically a triangle. And we know that the area of a triangle is 1/2 base times height, which is what you see here. And so g of 1 has a value of 3/2. Okay, now let's see what happens when we evaluate g of 2. G of 2 is the integral from 0 to 2 of f of t dt. So again, these linearity properties of integrals allow us to break this up into two separate integrals. I have the integral from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt. Well, we already did this one in the previous example. We know that has a value of 3/2. And this one, well, that's just a rectangle from 1 to 2. It has a width and a height, and we can easily compute the area. So the width is 1 unit, the height is 3, so it's just 1 times 3. So we have 3/2 plus 3, which gives us a value of 9/2 for g of 2. Okay, for these next couple of examples, we're going to use the bottom part of this theorem, which says that if g of x is equal to this integral, then g prime is just equal to f of x. So you're not actually taking the antiderivative here. You're basically just taking the function as is and assuming you're plugging in the upper limit of x. So let's apply that to these here in blue. So I have g of x is the integral from 1 to x of the square root of 1 plus 2t squared dt. Find g prime. So g prime is just the integrand evaluated at x, so it's 1 plus 2x squared. And again, that's because integration and derivation are opposite operations. So if g is the integral, g prime is just what you're taking the integral of. You're not actually taking an antiderivative because that would be integrating, not deriving. So here's another one. G of x equals the integral from 0 to x of cosine of 3t squared. By the way, this lower limit doesn't matter as long as it's a constant and it's within the domain. So I have the integral from 0 to x of cosine of t squared. And again, if I look for g prime, that's just cosine of 3x squared. The x replaces the variable t. Okay, but it is possible for the limits to be a more complex variable expression other than x. So if it's something other than x and you have variables in your limits, then you have to use chain rule when you are finding the derivative of the integral. So this next example allows us to illustrate that. So I have g of x equals the integral from 1 to 3x squared of t squared dt. So we're going to let u equal this new upper limit that's 3x squared. So then that means I can rewrite g of x as g of u equals the integral from 1 to u of t squared dt. So now I have to take the derivative of both sides. So that gives me g prime of u. And I have to take the derivative of this integral. So I have d du of the integral. But then don't forget that your u is something other than just x. It's 3x squared. So it has to be followed by du dx. So you can think of this as like chain rule. So the outer function, this would be considered the outer, and this would be considered the inner. A little different than what you're used to, but we also are taking the derivative of an integral. So it's not exactly the same as what we were doing when we were learning derivatives. Okay, so the derivative of the integral is just u squared. And du dx, well, that's just the derivative of this, which is 6x. So that's what you see here. So we have 3x squared to the second power because u gets replaced back with 3x squared. And du is 6x. So we get 9x to the fourth times 6x, which gives me a final result for g prime of 54x to the fifth power. Okay. So in general, if you have limits that are functions of x, and it is possible for both the lower and upper limit to be functions of x, so I'm calling them u of x and v of x. So if g of x is the integral from u of x to v of x of f of t dt, then the derivative of g prime, is f of v of x. So in other words, plug in the upper limit times the derivative of the upper limit minus f of u of x, plug in the lower limit, times the derivative of the lower limit. So this looks kind of like part 2 that we did earlier, where you're plugging in upper limit and lower limit. Okay, so let's do an example like that where my limits are variable expressions. So I want to find g prime of x for g of x equal to the integral of sine of x to cosine of x of 2t dt. Okay, so g prime is here. G prime of x is 2 cosine of x. So the cosine replaces the t, so that's where this comes from, times the derivative of cosine, which is negative sine, minus, because again we are subtracting, then it's 2, and then we have to plug in the lower limit, so that's where we get this, 2 sine of x, times the derivative of sine, which is cosine. That's what you see here. So in the second line of this problem, I just multiplied the first term. So that gives me negative 2 cosine x sine of x minus 2 sine of x cosine x. These two are like terms, so your final result for g prime is negative 4 cosine of x sine of x. Okay, so now you should be ready to try the homework. Good luck.